This chapter has many drawings which I can't reproduce here, so I'll concentrate on some of the problems. A prime mover is anything that can exert a force on a generator causing it to turn. The prime mover could be water, steam, gasoline or diesel engines, or even wind. If the prime mover is exerting a torque and it causes a speed, then we can calculate the mechanical power. The formula for mechanical power is speed times torque divided by 9.55, and the answer will be in watts. Notice that 746 watts equals 1 horsepower. The output of the generator depends on the speed and the voltage constant. The voltage constant is given by the manufacturer, and it relates output voltage to speed in revolutions per minute. In this example, we have calculated the output voltage, and we notice that if the generator is turning faster, then we'll get higher output voltage. The frequency of the output voltage is determined by the speed and the pairs of poles on the generator. We have used the term alternator instead of generator to indicate AC, but it doesn't really matter. Any term is good. The torque produced by a DC motor depends on the torque constant and armature current. The torque constant is given by the manufacturer, and it relates torque in Newton meters to armature current in amps. In this example, with the given torque constants and 3 amps of armature current, we have calculated a torque of 0.6 Newton meters. We use the conversion factor to go from Newton meters to foot pounds. Notice that most people say foot pounds, but it should really be pounds foot according to our book. If the DC motor using 3 amps is spinning at 1800 RPM, then we have mechanical power. We calculate mechanical power, which equals speed times torque divided by 9.55, and we find in this example that we have produced 113 watts of power. We use the conversion factor that 746 watts equals 1 horsepower. Then we can convert 113 watts to 0.15 horsepower. In this example, we have a DC motor with armature resistance of 2 ohms and a voltage of 120 volts DC, which means we have a starting current of 60 amps. Next, we use the torque constant and starting current to calculate the torque, which in this case is 24 Newton meters. Again, we use the conversion factor to convert from 24 Newton meters to 17.7 foot-pounds. This is for our convenience. This example shows that a DC motor has a very high starting torque, and so it is ideal for electric vehicles or other heavy loads that has to be put into motion.